Welcome to this demonstration of linear buckling analysis in Autodesk Nastran in CAD. Buckling may occur in areas of design where there's a loss of stiffness due to compressive loads. It is often dangerously overlooked and can be analyzed right here inside Inventor. During this video, we're going to find out if the material we're using for the crane does not yield and ensure the model not buckle under a 20,000 Newton load. We're only going to run the solver on the boom by itself, so we'll hide the other components. Now that we have just the parts of interest, we will generate a mesh on these parts, using 3D solid elements and using welded contacts to hold the different parts together. Now we'll apply some of the boundary conditions that simulate the real-world scenario. We're going to start with a fixed constraint on one end of the crane. Then we have two holes used for the actuator that is lifting the boom up and down. In order to simulate a bearing, we'll add rigid connectors from the nodes on the model to the center of the hole. We'll put a connector in each of the holes. The two center points can now be used to apply a constraint that can rotate but does not translate. Notice there are options to allow translation or rotation in any of the 6 degrees of freedom. Finally, there is a force from lifting an object. The load will be applied in the direction of gravity, which in this case is the Z direction. Following the run, the results for the static load can be examined. However, rather than examining the von Mises stresses shown here, let's look at the normal stresses and focus attention on the compressive stresses. Under the steel tubing, we see we have almost 100 megapascals of compressive stress. The material won't yield here, but it might cause a buckling failure. To find out, we'll do a buckling analysis, which can be set up and run right here in Inventor. By changing the study, we're simply adding a subcase so we can view the stress and buckling results in the same analysis. The boundary conditions for the linear static study can simply be dragged to the new subcase. The buckling analysis will result in a list of eigenvalues. These are scale factors on the applied load that indicate the actual buckling load. The first one for this model is just over 2,600 newtons. Since we wanted a minimum of 20,000 newtons, this is clearly a problem, and we may want to make modifications to the model dimensions to avoid catastrophic failure for larger loading conditions. This workflow not only saves time and money during the design process, it also ensures a safer product and fewer warranty claims for the customer. Autodesk Nastran in CAD helps to make better products using digital prototyping.